In order to calculate the heat transfer rate across a flat plane solid, you need to integrate Fourier's law in the direction of heat flow, from position x1 to x2, which also corresponds to a temperature T1 to T2 respectively. If the heat source on the left-hand side of the flat plane has been supplying a steady rate of heat, while the heat sink on the right-hand side has been sucking in the heat at the same rate for some time, Q will be constant. The system will be said to be at steady state. The thermal conductivity of a solid, or liquid, substance, depends on the temperature of that substance. However, if the difference between T1 and T2 is not too large, the thermal conductivity can be considered to be constant. At x1, the heat transfer area will be the big surface turned away from U, and is equal to breadth times height. Even at x2, the heat transfer area, here turned towards U, is also B times H. The heat transfer area remains B times H at any position between x1 and x2. Of course, you will be neglecting the slight increase in area at x1 due to the higher temperature, which may cause the solid to expand a little bit. However, chemical engineers, in general, try to make things easy by making simplifying assumptions. If you think it is reasonable to assume that the heat flow rate, the thermal conductivity, and the heat transfer area are constant, you can take these out of the integral signs. The integral of dx is x, and of dt is t. Integrating between the limits of x1 and x2, which correspond to temperature T1 and T2, you get the following. You can make Q the subject of the formula again. You can rearrange the equation to get Q in terms of R, the thermal resistance. You can regard T1 minus T2, which has a positive value, as the driving force for the heat transfer. From R, the thermal resistance, you can see that if the solid is thicker, and x2 minus x1 is larger, the resistance to heat transfer will be higher. However, if the thermal conductivity, or the heat transfer area, is higher or larger, the thermal resistance will be lower. This makes sense, does it not? This slide will show you how to calculate thermal resistance for a flat plane solid of size 4 meters by 3 meters by 2 meters. The thermal resistance depends on the direction of heat flow. Consider what happens to x2 minus x1 and the area A if the heat flows from the left. x1 and x2 are where the heat enters and exits the solid rectangular block, respectively. What is the value of x2 minus x1 in the thermal resistance expression? If you thought that x2 minus x1 was 3 meters, you were correct. What about the value of the heat transfer area, A, in the expression for thermal resistance, R? This area is perpendicular to the flow direction of heat, and just about the same at any given value of x, from x1 to x2. If you thought that the heat transfer area was 8 meters squared, you were correct. Now, what if the heat flow was from the front to the back? What would you calculate the values of x2 minus x1 and area to be? If you thought delta x was 4 meters, and the heat transfer area was 6 meters squared, you were correct. Now, how would you calculate the thermal resistance, if the flow of heat was from the bottom to the top? Discuss your answer with your fellow student. If you do not feel like doing this, consider that discussing challenges is an important part of being a chemical engineer. You can also calculate the thermal resistance of a cylindrical solid, in a similar way, using Fourier's law, but in a radial direction, so that you write the law in terms of R, not X. You can deduce the area, A, in Fourier's law by bending a piece of paper, with area on the one side of L times B, to form a cylinder, as depicted in the diagram. The area of the one side of the paper forms the heat transfer area of the cylinder. The circumference of the cylinder end has a value of 2 times pi times r, and this is then equal to the one side, B, of the paper. You can see that the area of the one side of the paper, which is B times L, is equal to 2 times pi times r times L. This is also the heat transfer area of a cylinder. A depiction of heat flow in a cylindrical solid is shown. Heat is generated in the central dark rod-shaped core. The generated heat flows radially outwards, through the cylindrical solid, as shown by the arrows. The depicted heat flow occurs throughout the length of the cylinder, which is why you use the heat transfer area, 2 pi RL. You can apply Fourier's law to a thin slither of cylinder, from where the radius is r, to r plus dr. The heat transfer area across this small increment remains 2 pi r L. Similar to the flat solid plane, you can now integrate Fourier's law from the inner radius, r, I, to the outer radius, r, O. This is from a heat source to a heat sink, if the heat flows outwards. Note that r has been moved to the left-hand side, the dr side, so that the variables are separated, as required in integration. This slide has shown you how to determine the thermal resistance of a cylindrical solid. T, I, minus, T, O, represents the driving force for heat transfer. Your homework today is to derive the thermal resistance through a spherical solid. In this slide, you will see how to calculate the thermal resistance of flat plane solids in series. Solids are in series with respect to the heat flow, if the heat flows through the one solid, before flowing into the next one. In the animation, the heat flows through solid with thermal resistance 1, R1, then through solid with thermal resistance 2, and then finally through the lost solid. Hence all solids are in series. For each thermal resistance, Q can be related to the driving force, using the thermal resistance as shown. The driving force for heat exchange can be made the subject of the formula for each solid. If you add the left-hand sides of the equations, you get T0 minus T3, which is the total temperature drop. If you add the right-hand sides of the equations, and take out Q as the constant common factor, you get Q times the total thermal resistance. Making Q the subject of the formula, you see that this is equal to the total temperature drop, actually, minus delta T. This total driving force is divided by the total thermal resistances of the solids in series. You have now come to the end of the session on conduction specifically.